Yeah, hello together. Um, to our statistics lecture. We started the last time with inequality metrics and we introduced the measure of the concentration ratio, a quite simple measure if we calculate market shares or if we calculate the part of the income a specific part of the population has, then we calculate just the proportion of the largest firm or the richest people with reference to the total income or to the total market size. And for this, in general, one calculates CR1, CR2, and CR3 with the three largest firms. Um, Another measure was then the so-called Halfendal Index, where we took the single market shares of the firm and we just squared these market sizes. And as I mentioned in statistics, we quite often use these squaring of our variables. If you remember, for example, the squared distance from the mean, which we called the variance. And so also the Halfendal Index is a widely used measure in this inequality matrix. And yeah, if we interpret this, then if we write it as market share times market share, then we could say that we have the market share itself times another time the market share. So we can interpret the market share also as a weight of this specific firm, and therefore we can say that a larger firm is overestimated since a larger firm has then also a larger weight. And then we can interpret this measure as, of course, if the Halfendal Index is 1, then you have a single firm or a single person which more or less has the total amount of the income or the market, and therefore we can interpret this as a monopole. And if everybody has the same income or if every single firm has the same market share, then of course the Halfendal Index becomes 1 over n. And if we have many firms, then we can interpret this for something like a highly competitive market. And this Halfendal Index especially is widely used in economics and also here in politics, where this can be interpreted as the effective number of parties. Then we calculated this with some examples, and then we started with another inequality matrix, or more better we better say a graphical visualization of inequality, and this is done by the Lorence curve. And yeah, so to speak, we represent the inequality of a distribution with the reference to the uniform distribution, since we just calculate, as we have done in the market shares, the concentration ratios. CR1, CR2, CR3, and so on. So just the accumulated concentration ratios, and we plot these concentration ratios against the uniform distribution, and this is Fi, so just adding up all our numbers, or in an income distribution, adding up all our people from the poorest to the richest people, the number versus their accumulated income, and then we obtain data points moving from 0, 0 to 1, 1. So 1, 1 is then the total population or the total market, and they of course have the total income and or the total market size, and therefore we end up at 1, 1. And we also just use our examples we already had, and there we saw that in this case where we have a slightly skewed distribution, that then the Lorentz curve moved outwards. And now we want to look also at our other examples, and this of course we will also do in Excel. Oops. Statistics. And I think we did it. Yeah. So let's put this again that you can see it. Like this. So maybe you have tried this at home. So again, now we take the uniform distribution. And let's put this. And now again, we ask, what is Fi? Fi is of course just accumulating these numbers. So we calculate 1 over 5 and fixing this number with the dollar signs. And here, if we have a uniform distribution, we obtain a very surprising result here. So which numbers do I obtain if I have a uniform distribution, if every firm has the same market size? This I even do not have to calculate. I just can look it up. So what is the market size of the smallest firm? What is the market size of the 2 smallest firms, 3 smallest firms, and so on, if every firm has the same market size? Any? Yes, of course. So, so I could calculate this by dividing 200 by 1,000, or since I know that it is a uniform distribution, then I can just copy these numbers to the right, or that you are not confused that I have now another formula. Let's do it if we wouldn't have a uniform distribution, and we have to fix 3 dividing by 1000. And then hopefully this works, that we go down. Yes. Oops. Copy. And then very surprisingly, this ends up in which kind of a Lorentz curve? Of course, just our 45-degree line. So that you can see this. Oop. So here we have it, and then let's also copy some this over here. Into our slides. So, numbers. Is it not possible? Yep. And the Lorentz curve. And even so here also write this down here. This would be Fi, and here we have Ci. Oh, the other way around. Let's also see something. Sometimes this is interchanged. Therefore, we have to look. X is C, we see here, and Y is T. Okay. Let's put it also down here. So this is then, of course, we obtain, of course, a straight line from 0, 0 to 1, 1. So, example C. How will it look? How will it? Oops. Yeah, I have already the numbers. So, how will the Lorentz curve look like if we have a monopole? What would you guess? this has to be one further on. So if you make a guess, if you should just describe the Lorentz curve of a situation with a monopole or with only one very rich guy in your society. Fi, what would you think? So you have to start at first with the first firm. This would be here, 1. And what is the market share of this firm? Of course, 0. Then we have 2, 0, or 1 over 5, 2 over 5, 3 over 5, always 0, 4 over 5, and in the end we have 5 over 5. And in this case, we have our total market share of 100%. So in this case, we have always here 0, and then we are moving up here at the 1. Let's do this also in Excel. For this, since I want to use again the same format, I just copy this because then I just only have to interchange my numbers. So this would be then 0, 0, 0, 0, and 1,000. And so we obtain this Lorentz curve, and we wanted also to plot this relative to the uniform distribution. So let's add C and again C. Oh, I used the wrong one. Data and adding C and column C. Here also 1. This looks nicer. And also here only 1. So first we need the numbers. And the Lorentz curve. So in this case, if we have a monopole, the Lorentz curve moves extremely to the right. And in the end, we want to take our example with 10 firms. Well, of course, this we can also do, so to speak, brute force, that we just take these numbers here and calculating it in the same way as we did before. Let's do this a bit smaller that you can see it. Yeah. This worked. In order to have this nicer. So again, the numbers. Sum from 1 and fixing the 3 divided by 1000. No, not by, divided by 1000 divided by 10, so it's 12. And in this case, we just have to accumulate 30 plus 30 plus 30 and so on, divided by 1000. And for this, again, can just copy this formula down here. And divided by 13, of course. So this would be the method, I call it brute force, but I also have written down here only the 30, 150, and in the end the 200. And why did I do this? Of course, we have here in the beginning 5 times same size of the small firms, and here we have 5 times and 3 times the same size of all firms, and in the end 2 times the same size of all firms. And what does this mean for our Lorentz curve? Well, we could calculate this by calculating, or we could represent the Lorentz curve by calculating every data point for every single firm, but we know from 1/10 up to 5/10 we have 5 times 30 is 150. So all these 5 small firms have a total market size, an accumulated market size of 150. calculated market size equals 150, so 15%. So we would have here up to 15%. And how does it look like? How does the Lorentz curve from 0 to 1/2? How does it look like if below this all firms have the same market size? What I have to draw between 0 and the data point 0.5, 0.15, if every firm has the same market size. Any idea? Well, if we go back to our example where we have the uniform distribution. So now we have a subset where we have a uniform distribution. So with which kind of graph do we end here? What do I have to draw? Do I have to draw between 0 and this first data point? Well, I'm moving up to the right, always the same amount, 0.1, 0.2, 0.3, 0.4, 0.5. And I'm moving up on the vertical axis, 0.03, 0.06, 0.09, 0.012, and 0.15. And if I'm moving up to the right always, in the same step, and I'm moving upwards the same steps, then I end up with just a straight line. So, and then I have the next three firms, 150. 3 times 150 is 0.45 plus our 15% means that here at 8 over 10, because then I end up at the 8th largest firm, and accumulated market size of the first 8 firms adds up to 60%. So this is 60% of the market. So I put it here, 60%. And then again, I just draw a straight line between this data point and this data point. And in the end, well, let's go a bit higher here. So one would be, let's say, here, 100%. And the last two firms with a market share of 200, they add up then the missing 40%. just to 1. And this would be again if every single firm would have a market size of 100. So in this case, we could then calculate this if we do it for every single firm. Then oops, what did I hear? Anything wrong? This is wrong, I think. Oh, over 200, so here I need an A. Still not right. A3 over A12 should be right. And sum these two over A12. Oh, these are the numbers. So I need here only the number. Because these numbers are already added up. So the 2 is the second firm, and then I have 2 firms. So this has to be done like this, and now I should obtain the right Lorentz curve. Yes. And here we see this, that we here have the straight line, here straight line, and in the end the straight line. Again, a bit smaller, but you can see it. And relative to the uniform distribution would mean this and this. Nee, bitte, komm. Hoppala. Again, formatting the axis. And the title. CI and FI. So and our plot. Obtain it here. So I think it was not too bad. It looks almost like this. Of course, if I ask something like this in the exam, then of course you can also draw a diagram like this by hand, and this has not to be in the exact form, I just have to see that you have understood the idea. Okay, but in order to be complete, let's also take one time the other table that you can see that in this case we have the same Lorentz curve, because then we have here I need another column, and this were 5 times, and this were 3 times. Oh, here are the counts, sorry. So 5 and 3, and these were 2, but then we have here 1,000 is total market size. So in this case we obtain equals 5 over 10, and here 8 over 10, and in this case we have to calculate 5 times 30 over total market size, and here 5 times 30 plus 3 times 150 closing brackets divided by total market size, and this was Fi and Ci, and if we plot this, hopefully we get the same Lorentz curve. Oops. What did I do wrong? Oh, here, not the 0.5, but this has to be a B here. And then we have the same Lorentz curve. And again, oh yeah, do you see it? Title Ci and Fi. And also 1. Okay. Oh, that's relative to our uniform distribution. This one and this one. So these are then, of course, the identical Lorentz curves. Okay, and of course you can calculate it for every single firm, or if you do it the faster way like this ends up, of course, always in the same picture. Okay, this is just the graphical representation, and if we summarize our properties of our Lorentz curve, then of course we can say, since we're always moving to the right, we at least if there is a new firm with a higher market size, then we always move to the right and we're moving up a little bit. So our Lorentz curve has, of course, to be monotonically increasing. And if we don't have this uniform distribution, then this means always that if we go to the right, that in this case, since we have at the beginning poorer people, then we are not going that much up as we have went to the right, and therefore in the end we come to the very rich people, and then the Lorentz curve will be very steep, and in addition, of course, we obtain a convex Lorentz curve. This I had to translate. So in between, if we have people or firms with the same income or market size, then in between the Lorentz curve is linear. This is just the case we had here, that we had here a linear part, we have here a linear part, and we have here a linear part. And if you identify within the Lorentz curve linear parts, then of course you know that within these linear parts, the firms or the people have the same share of the total distribution. Of course, this we already mentioned, the Lorentz curve is in between 0.0011. Then we had a straight line from 0011 if we have the uniform distribution, and in the monopole case or in the extremes case, then we would have this Lorentz curve CIFI, which moves very much to the right, or if we move then to the case in the limit when n goes to infinity, n moves to infinity, then we would have this extreme Lorentz curve that we just go to the right up to 1 and we end up also in the 1. So just stepping up from 0 to 1 in the end. So if m moves to infinity. And of course, we always plot the Lorentz curve relative to the uniform distribution. Oops. So these are then again our examples, and now with these Lorentz curve, then we more or less can have a look to income distributions, and here some other examples. Again, one time the uniform distribution, straight line. If we have a right skewed distribution, here is our example that the poorest quarter of a population has only 10% of the total income. Then we move with our Lorentz curve to the right, and here I call this the Bill Gates distribution. If you take a small country and Bill Gates, the founder of Microsoft, would move into this country, then maybe he accumulates 97% of total income in this small country, and then we had already seen we have this Lorentz curve that we move very much to the right in such a distribution. So, and now we want not only graphically represent this kind of distribution, but we want to have an aggregated measure like our concentration ratio we had before, which can describe how unequal is our distribution. And this measure can now deduced from our Lorentz curve, and this measure is called the Gini coefficient. And what do we do with our Gini coefficient? Well, remember, we have our Lorentz curve relative to the uniform distribution, 1 and 1. And let's assume our Lorentz curve would look like this. Then, of course, we can calculate the area between the Lorentz curve and the uniform distribution. Right, because you don't see me, so that is better. And of course, if we have a really unequal distribution, let's assume something like this. In this case, this would be the area. And so if we divide this area here by the total area, so the extreme distribution where only one single person accumulates the total income in our population, then in this case, dividing this area by the total area, we would obtain, of course, 1. And if we take only the uniform distribution, so Lorentz curve would lie on the 45-degree line, then in this case we would have no area dividing by this total area, and then the Gini coefficient would be then the Gini coefficient would be 0. And since we know that this is just a triangle with these two sides and here 90 degrees, we know that this total area would be 1/2, and therefore we obtain that the Gini coefficient is then 2 times our area F, and this area F I gave you on the next slide, that we just have this area here divided by the total area here. And this is then, oops, this should be GC, our Gini coefficient. And then, of course, we can say that GC is in between 1 and 0, and if we have GC equals 1, then we have, or if GC is in the neighborhood of 1, then we have a very unequal distribution, and if we have a low Gini coefficient, so in the neighborhood of 0, then we have a quite equal distribution. So, and now we want, to calculate. Here we are, our Gini coefficient. And how do we have to do this? Of course, then let's take another picture here. Or let's take this one. So if we take this example we have here, then this would be F1, this would be F2, and this would be also F1. If we go up here, this would be F2, and here we have C1, and here we have C2. So what we have to calculate is then this first area. Let's call this L1, L2, and this area L3. How can we calculate this? Well, what is L1? L1 is just this triangle here. And here, of course, we have F0, C0. And what do we need? We need the area of the triangle. What is the area of a triangle? This is just baseline times height divided by 2. So what we obtain here is 1/2. What is the baseline? The baseline is this one. So this would be F1 minus G1. And what is the height of this triangle? Well, the height is just from here to the extreme point here, and we have to yeah, measure this with the 90-degree angle. So from here to here, so this would be F1 minus F0. And now maybe comes the harder part, that we have to calculate this area here. What is L2? What kind of a geometric form is this green part? Well, these two are parallel. And if these two are parallel, then of course we have a trapezoid. And the area of a trapezoid is, if we call these two parts A and B, this would be 1/2 of A plus B times the height of this trapezoid, and this would be this one. So we obtain again 1/2 times 1/2 of F2 minus G2 plus F1 minus G1 times the height, and the height is again F2 minus F1. And the last part, let's take this in red. L3. This is again our triangle here, and this would be the height of the triangle, and this would be the base line, and therefore we obtain 1/2 times the baseline F2 minus G2, F2 minus G2, yeah, times the height, and the height, if we call this F3 and the 100 we call G3, these of course are 1, and in order to be complete, this is 0 and this is 0. Es geht gerade, nee, geht gerade nicht auf. Komm. Ja, kannst du. Yeah, so, yeah, my sons have holidays. So, and the height was F3 minus F2. So this area we have to calculate. So then we obtain the GC is L1 plus L2 plus L3 over 1/2, because we have to calculate this relative to the total triangle. So this one is of course 1/2. And yeah, this we will do in an exercise. In general, of course, we do not have also only these 3 areas, especially we have to know how to calculate the area of a trapezoid. In general, we can, oh, I always miss this. What we will do in an exercise is that we in general could calculate the Gini coefficient with this formula, or that these two formulas are even equivalent. And what we can start now is, yeah, let's take the first example which we had, that we should calculate the Gini coefficient of our first distribution. So let's take this as we have here. And we had already, I think, the FIs and the FGs and the GIs. So let's move here. No, this was, yes, this it was. So let's put these numbers here in it. And let's take this formula here. And then let's start to calculate our Gini coefficient. Gini coefficient would be then 1 minus, what do we have to calculate it first? Sum over Fi minus Fi minus 1. Again, we have here F0 equals G0 equals 0 as convention. What do we have to do? Well, you just have to use this formula here. Do you know what a summation sign means? This one here? Hopefully. This you should have done in your statistics and mathematics courses. Well, we just start at I equals 1. So if I equals 1, then we have F1 minus F0 times G1 plus G0. And since we have here the sum, we need a large bracket here. So plus F2 minus F1 G2 plus G1 plus F3 minus F2 times G3 plus G2 plus F4 minus F3 times G4 minus G3, and in the end plus F5 minus F4 times G5 minus G4. So I will not put every number inside here. Then we obtain GC equals 1 minus 0.2 minus O times 0.7 plus O and 0.4 minus 0.2 times 0.19 plus 0.07 plus, and so on. And then we obtain the Gini coefficient. Well, of course, this we can do by hand, and of course, we can also calculate this via some statistic software, and this we will do also today in the end of our lecture. Copy and put it here. This would be then Gini 1. So what we need is Fi minus Fi1 and Gi plus Gi1. So Fi minus Fi minus 1, and we need Gi minus Gi minus 1, and we start here, equals this minus this, and 0.07 minus 0, and we move this down here. Oops. Oh. So what we need then is we have to multiply these two numbers. So into this formula here. So this times this here. So these two equals 0.2 times 0.07. Copy. And in the end, we need the sum of all this. So sum adding up is 0.2, and finally 1 minus Gc equals 1 minus 0.2 is 0.8. So what we then obtain is that this one is 0.2 and Cc is 1 minus 0.2 is 0.8. I think, is it exactly this? Let's see. Yes, okay. So then we are done for today, and yeah, maybe you can try also to calculate the Gini coefficients for our other examples. Then see you next week.